So I'm continuing part 2 with home exercise 2, and you will see in this example both the standard method and the Lagrangian method is used. So you are given the following information below, and you are told to calculate the quantities of good X and good Y to be consumed. So you need to determine how much X and how much Y will be consumed subject to a budget constraint in order to maximize utility, right? So here's the following information. You've got your income, the price of good X, the price of good Y, and your utility function, right? So using the standard method, you first need to get your marginal rate of substitution over there, which is the ratio of your marginal utilities. So to get your marginal utility of good X, right, over there, it is the first order partial derivative of the utility function with respect to X, right, treating Y as constant. So therefore, if we just go back, there's our utility function. So if I'm going to get my first order partial derivative of this function with respect to X, it is going to be 0.8 times 6 times x, and now x is raised to the power of 0.8 minus 1 times y to the power of 0.2. And that is what we have over there. That becomes x to the minus to the power of minus 0.2. So therefore that is 6 times 0.8 is 4.8. Y to the 0.2 is in the numerator, but x to the negative 0.2 can be written in the denominator. And similarly, you could get your marginal utility of good Y, and that is the partial derivative of your utility function with respect to Y, treating X as constant. And this would be your marginal utility of good Y. I'm not going to go through that now. So therefore, the ratio of these two is going to be given as your marginal utility of good X divided by your marginal utility of good Y. Now, of course, we can make our lives a bit easier by inverting this. We can multiply it, and therefore we can invert that side. Therefore, you can just add the powers of your variable y. So 0.2 plus 0.8 is 1. So that's just y to the power of 1. And you've got in your denominator now 1.2 x, because 0.2 plus 0.8 is going to be 1 as well. So therefore 4.8 over 1.2 is just going to be 4 in the numerator. So you have 4y over x. Then you also have your price ratio, which is the price of good X over the price of good Y, and the respective prices were 4 and 9. And then that is your budget constraint. So now you know your next step was to set your MRS, which was the ratio of your marginal utilities, equal to the ratio of the prices over there to determine the optimal bundle or mix. So therefore, I can now substitute x is equal to 9y into your budget constraint, and you can solve for y and x and your utility respectively. So take note here. Your y was equal to 20, x is equal to 180, and your utility is equal to 695.9455. And this is using the method you learned last week. Also, you are preparing this method for your module test. Now, an alternative method is the Lagrangian multiplier method. So the method says, let's just scroll down, right, that you need to first define a new function. So this is the information that you were given. So there's your objective function, which we can see is placed over there, plus lambda. And in brackets, we have our constraint that is just rearranged. So you have your constant minus that phi portion. Phi is a function of two variables, x and y. So remember, if we go back to our budget constraint quickly, you saw that your budget constraint was written as 4x plus 9y is equal to 900. So of course, if you rearrange that, it could be 900 minus 4x minus 9y, because you've set the left-hand side equal to 0. So 900 minus 4x minus 9y, that is your constraint. So now we've got our new function, our Lagrangian function. So the next step is to get our three first order partial derivatives of this function with respect to x, y, and lambda. So just be careful with your exponents here. So therefore, if I get my first order partial derivative with respect to x over here, I can see that I've got 0.8 times 6 is going to be 4.8. I know that x is going to be to the power of minus 0.2, so therefore I can write it in the denominator as x to the power of 0.2, and I still have y in the numerator as y to the power of 0.2. Right? Now, if you were to multiply out here, you would get 900 lambda. You get minus 4x lambda minus 9y lambda. So there's your next term, minus 4x lambda. And of course, you differentiating with respect to x. So although this step isn't shown us multiplying out here, just bear in mind that you would have minus 4x lambda and I have to differentiate with respect to x. So therefore, I've got minus 4 lambda. And I set that equal to 0. So you can see, therefore, if you rearrange making lambda the subject of the formula, that minus 4 lambda would go over to the other side and the sign would change, and then the minus 4 can just go into the denominator. So we've made lambda the subject of the formula there. Similarly, get your first order partial derivative of this function with respect to y. So let's differentiate where we see y. So I've got 0.2 times that coefficient. It's just 1, so still 0.2 times 6 is going to give me 1.2. I have x to the power of 0.8, but y is now raised to the power of 0.2 minus 1. You have to say n minus 1. That will give you minus 0.8. So of course I can put that in the denominator. So I have y to the power of 0.8. From our rules of exponents, I can express it in that way. And of course, if we were to multiply out here, you would have gotten 900 lambda minus 4x lambda minus 9y lambda. So there I know I'd be left with minus 9 lambda, right? And set that equal to 0. And again, you're going to rearrange, making lambda the subject of the formula. And then lastly, your third first order partial derivative of your new function with respect to lambda. Remember, it is simply going to be what is in that constraint, because had you multiplied out, you would have gotten 900 lambda minus 4x lambda minus 9y lambda. And of course, getting your first order partial derivative, you differentiate wherever you have lambda, and you'd be left with 900 minus 4x minus 9y. And now you can set that equal to 0. So the next step now is we can solve simultaneously. So I can equate those two. There you can see we've equated those two. So now you can solve. And if I multiply that, I'm going to get 4.8 times 9. The exponents would end up being added. So that would just give me y to the power of 1. And 4.8 times 9 is 43.2, and here I'm going to have 4 times 1.2, and that's going to give me 9. And again, my exponents can be added, so that is just going to be x, right? So therefore I can rearrange, making either y or x the subject of the formula here. It's easier to make x the subject of the formula because 43.2 divided by 4.8 is going to give you 9y. Therefore, I can substitute x is equal to 9y into that third equation over there. X is equal to 9y. Substitute that in. That's going to give me 900 minus 4 times 9y, that's minus 36y, minus 9y, that's going to give you minus 45y. If you take that over, it becomes positive. Therefore, y is 900 divided by 45. And what do you notice? Y is equal to 20. Similarly, x is equal to 9 times 20, 180. And if you substitute your combination of y and x into your utility function, you get the same answer of 695.9455. So this is a somewhat faster method to solve for x, y, and your utility. Now, if we just plot this, we can see our quantity of good y was 20 and our quantity of good x was 180, and that point of tangency is given over there. And you can see that our utility is equal to 695.9455. Of course, you could determine what these intercepts are by taking your income and dividing it by the price of good y in that instance, and over here taking your income and dividing it by the price of good x, and that would give you your intercepts. Right, so that concludes the Lagrangian multiplier. So before we continue with partial elasticity, please remember to work through the examples step by step. Okay, it is very important that you practice and understand how to express that new Lagrangian function, and also how to determine your three first order partial derivatives of that function and then solve simultaneously. So we'll continue part 3 with partial elasticity.